All right,
Is
we
it in
can
my
see your
slide?
slides. Yep,
Excellent.
take it
All
away.
right. So I'll just build on what Jamie and Kathy have already discussed with space weathering, a chemical alteration and physical process that occurs on the surface of airless bodies. In prior Apollo samples, Michelle Thompson noticed that the nanophase, typically nanophase iron that we find in the rims on material were actually showed some oxidation. They were Fe2 plus and even in some cases Fe3 plus. And we wanted to study this oxidation effect with these unique samples, especially curated samples, because in order to understand space weathering processes on the surface of the moon and how they occur, we also need to understand what kind of curation alteration might be inducing the effects. When Michelle looked at her samples, without being able to conclusively know they haven't undergone any alteration during the last, at that point, 47 years of curation, we couldn't conclusively show it was the oxidation occurred on the moon or occurred in the lab. So looking at these ANXA samples allows us to have some insights into that. And the way we are analyzing the samples are using X-ray absorption and X-ray emission, using the SLAC National Accelerator Laboratory with my co-authors Roberto Colina-Ruiz, Dimos Sarakis, and Tom Kroll. And we're pairing that with TEM data, TEM analysis, and using electron energy loss spectroscopy, or EELS, and using that as an equivalent but much higher spatial resolution than the X-ray absorption at SLAC. And the TEM work is being done by Hope Ishii and John Bradley at University of Hawaii. My contribution to this is looking at laser weathered materials as end members. We get different minerals that we expect to find in the core, such as pyroxene, olivine, anatase, or titanium oxide, quartz, and hematite, and giving us laser weathered, which replicates micrometeorite bombardment, and unweathered material to analyze. So here's an image of the lab. On the upper left, you can see a Apollo powder, which is a fresh powder ground from an Apollo rock, 68416, on the upper right corner of the paper. And in a more mature sense, an Apollo 16 soil, 65701, which has a very high mature I sub S over FeO value of 106. With the laser weathering that we do, in this case with San Carlos olivine, we use a material that's uncompressed with a grain size of less than 45 microns, and you can see an image of it in the top. The spectra are down below for the fresh material, that upper spectrum. And as we laser weather it, it gets darker and redder, and it loses the 1 micron absorption due to olivine, which is the way we typically describe how spectra change for lunar materials as they're exposed to space weathering. So that bottom lower image is of San Carlos olivine after the dual laser radiation for about 32 minutes. What I mean by dual laser radiation, why we do it, typically laser radiation to replicate micrometeorite bombardment is done with a very short pulse, 6 to 7 nanosecond, 1064 wavelength laser. And that creates a lot of vapor and some melt and creates spectral changes. But what I noticed in looking at the samples and comparing them with lunar samples is we don't make agglutinates, which is a fundamental component of weathered materials, where it can be up to 60 volume% of the lunar material. So this lower right SEM secondary electron image shows an agglutinate that we're able to make using this dual laser irradiation method. And what we notice is with the dual laser irradiation method, we not only get things that look physically similar because we create agglutinates, we're more effectively able to erase the fundamental absorptions at 1 micron or 2 microns for pyroxene, as you can see in the spectra on the lower left. All our radiations are done with loose powder and under a vacuum of 10 to the minus 8. We can also, in the middle image, you can see we can measure spectra of the material while still under vacuum before we break vacuum. And we can also do these irradiations from room temperature all the way down to 25 Kelvin. So we can replicate the interaction of radiation or micrometeorites from Apollo samples all the way down to samples we expect to find at the poles. And today I'm going to show results for our orthopyroxene and our San Carlos olivine laser weathered experiments. This is Zane spectra taken by Roberto at SLAC. And what we see in this energy region is the oxygen K edge for unweathered olivine, which is the black spectra. Olivine is the black spectra here. Unweathered is the dotted line, and weathered is the solid line. Or sorry, the weathered is the dotted line. And the pyroxene are the red spectra. So again, unweathered is solid, weathered is dotted line. And what we notice is there's a sharp increase at the 532 after we do the space weathering, and this feature is much stronger in the pyroxene band relative to the olivine sample, and this is probably due to the relative amounts of oxygen that are in pyroxene relative to olivine. And we think this is showing increased hybridization of the silica oxygen orbital, and it probably points to SI reduction of the material. And I just want to point out, Roberto will be giving a further discussion on this data, more in the sense of curation on Wednesday in the afternoon sessions. We can confirm this SI reduction using this time X-ray emission spectra. Up at the top, you see olivine, both the weathered and unweathered, and the pyroxene weathered and unweathered samples, as well as some other standards such as quartz, silicon carbide, and silica. And what we see in these K beta emission spectra is that there is an increase in the peak K beta at 1833 EV after space weathering. And again, we think this increase is caused by a reduction in the silica species or the oxidized species. Moving back to X-ray absorption, here we're looking at iron lines for L3 and L2 edge for unweathered and weathered pyroxene. You can see, again, the solid black is olivine that's unweathered. The solid red is pyroxene that's unweathered. The dotted lines for both are the laser weathered material. The blue lines, the blue vertical lines show the centers for the L2 and L3 features. And what we notice is a decrease in the peak intensity for both olivine and pyroxene, which shows that we have an overall iron reduction as we laser weather the materials. Looking at these samples under TEM and EELS, so the EELS spectra is on the left, and we have a STEM HADF image on the right, where we've mapped out the green image shows iron metal within that yellow area. The next image, the blue or cyan, is the oxidized Fe3 plus material. And then below is the iron 2 plus. And we see that there is a mix of materials in there. The Fe2 plus is probably in the glasses, as well as some of the Fe3 plus that is there, and iron metal associated with some of the nano iron blebs. The eel spectra, you can see for the unweathered materials, it's a sharper peak at a little over 705 EV. And as we laser weather the material for olivine and pyroxene, the energy spectra broadens and moves to longer wavelengths, showing a series of oxidation states that are still present. So this is still work in progress, and we're starting to do similar analysis on some of the ANCSA samples now. But for now, our preliminary conclusions are that both with the X-ray emission and absorptive spectra and eels, we see a reduction of iron using the laser radiation. We don't see oxidation for the actual nanophase iron through eels and HADF imagery. The X-ray absorption and emission spectra are more of a bulk measurement. Their area is more on the millimeter square area, but similar depths on the order of 100 nanometers or so. And we wonder whether one change or difference between what we're seeing in the samples that we laser irradiate versus samples that are exposed to the solar wind and on the moon is that solar wind heating and implantation of hydrogen might be the cause for the oxidized nanophase iron that Thompson saw in her 2019 paper, where you need that hydrogen to bond with some of the oxygen and take out or increase the oxidation state of the iron as it gets heated, and it might not be a preservation effect of curation. So our next step is to compare these results of the laser weathered material with some of the typically curated and ANCSA curated samples to see if we see similar features. And with that, I'll just take any questions or comments. Thank you.
Questions, Darby?
Just a clarification and an ignorant question. So when you're doing the before and afters on the pyroxenes, those are on single crystals?
For the Zanes, no, that's from about, kind of 10 milligrams, 20 milligrams of powder that gets spread out onto a sample holder.
And it's the exact same sample after?
It's the exact same sample in that I create a powder. I take a portion of that and laser weather it. So I send off 2 samples to Roberto to analyze. So they're the same starting sample, but only one gets laser irradiated.
Got it. The reason I'm asking is because those variations that you're seeing look a lot like the variations we see at the K edges with anisotropy. And I'm wondering, when you spread the powders out, if you're somehow inducing preferred orientation, because the beam is polarized, of course.
My guess is the way it gets spread out would be similar, but I see Roberto's on the line, and he's the one who actually puts the sample onto the holder. I don't know if he's available. You want to jump in, Roberto?
Okay.
But
yeah.
Thanks for the comment, Darby. It's something we will look into.
And another comment is that I'm wondering how it affects the magnitude of the difference between your befores and afters. So just another thing to think about.
Yeah, we want to be able to quantify that better. That's something we're working on, to be able to quantify the difference to kind of get an understanding.
Yeah, we wrestle with that at K-Edge. We sometimes end up normalizing at 3 different places in the spectrum to get them to act right. So yeah, you might want to think about that.
Okay, thank you.
Kate has a question. Back to Michelle.
Hey, Jeff, this is Kate. So 2 things for the TEM work. Was that a fib section?
Yes, that was a fib section.
Okay, just into the sample. And they did also before and after just of the substrate. That was the weathered and unweathered. Those were uniform materials.
Correct, yeah. So the weathered part was from the rim, and then yeah, the unweathered from the host or more internal.
Okay, cool. And then just as a note for the 532 peak, we
Yep.
see that appear in eels, and it's usually considered, it's associated with molecular oxygen, but then also OO bonds, which is consistent with reduction of other things that are there. But we see a peak like that appear in eels for a lot of space weathered materials.
Okay, cool. Thank you for pointing that out.
Hey, Jeff, it's Michelle. Really interesting work. One thing that we've seen since we published that paper, and something that Kate and her group have been working on a lot as well, is that the oxidized iron seems to be associated with specific nanoparticle morphologies. So not just your regular solid spheres, but we see a lot of hollow nanoparticles and core shell structures, and even some pitted and vesiculated ones that tend to be, in our experience, more likely to be oxidized than the regular spheres. So if you keep a lookout for those, maybe when you're looking through the ANXA samples, we could see if that holds true.
Thank you. Yeah, it's a good point that there's morphology features along with the oxidation features. The donuts.
All right, Jack?
I don't think it has a significant effect in these relatively young regolith zones, but in the older regolith, you have to take into account, as I've talked before, the alpha particles from uranium thorium decay, at least in the interior of the particles. The paper by Bowen et al. Some years ago, looking at pleochoric halos around biotite from zircon, found that nanophase iron was being produced by the alpha particles. So it's a significant factor, but I don't think it's a factor in these relatively young regoliths. A significant factor. It's there, but I just don't think it's significant.